So next, Jacob Asmat will speak to us about oscillations and social opinion dynamics with an agent-based approach.
Yes, so hello everyone, I'm Jacob, I'm from the University of Birmingham, and yeah, my talk is about oscillations in social opinion. So I know that a lot of people here are not from this background, so I'm going to try and build it up from the ground up, basically, hopefully assuming no background knowledge. So I'm just going to talk briefly about why we want to do this, about the field of opinion dynamics more broadly, about an important mechanism called bounded confidence that we use in our model and is widely used. And then I'll talk through our model and results, and then the outlook as well after this. So if we look at, this is data from YouGov, and we can look at the most important issues facing the UK. So this is a polling question that's asked quite regularly, and people are chosen and they are asked basically which issues do you think are most important facing the country? And as you can see, this doesn't look like it's a steady state. Basically, it goes up and down, and there are places where, for example, you can see the health spikes around where the COVID pandemic happens, which is what you'd expect. We also have this similar sort of thing around economics. So I'm sure we're all familiar with this sort of cycle in the economy, and this is the UK Consumer Confidence Index. So it's basically how positive people are feeling about the economy. This goes all the way back to like the 1970s, late 1970s, and you can see it's roughly periodic. There are peaks and there are troughs. Unfortunately, it looks like we're in a bit of a trough at the moment, but hopefully that will change soon. So that takes an average of people's opinions. So then if you look on the individual level, you can try and track individual people's opinions and then try and track how they change over time. So we could just see an example of this happening here, and then put this onto some sort of graph that tracks their position over time. So in the case of the Consumer Confidence Index, this would be how positive do you feel about the state of the UK economy, for example. So the two main results in the field of opinion dynamics traditionally are these two steady state results. So if you track these people and you see how they change over time, letting them influence each other as well, then you tend to either get towards a consensus where everyone shares the same opinion, or segregation, sometimes called polarization, where there's sustained disagreement among these different groups of opinion. So we can model how these opinions change in different ways. There's a sort of top-down approach where you can assume it almost like a field and use a differential equation across it all. And these work best if you can assume sort of infinitely many interactions across increasingly small time differences. And then these individuals will interact constantly with the entire population. But what's probably more popular in the field at the moment is agent-based models, which I'm sure many of you are familiar with, where you look at the individuals and apply these certain simple rules to individuals and see how that affects the population level dynamics. And something which is nice about this is that you can change the order and the range of the interactions, basically, which we're going to talk about in more detail. And then just as a brief aside as well, agent-based models in general, what's quite nice about them is they can map certain behaviors across different disciplines. So this was a nice example I just saw in a paper where there was a mapping of bird murmurations, so when the birds are flocking together, and magnetism in a material. So these sort of like phase changes and behaviors that you see can sometimes be applied across fields, which is very nice. So in terms of the agent-based modeling approach to opinion dynamics, there are different traditions, and these come from different fields, which is why it's quite interesting to be in an interdisciplinary conference, because a lot of the models are influenced by the field they come from. So there are these sorts of models. This is a very famous one called Boyd's, where it's trying to model the movement of birds, for example. And there are other ones which approach more from the physics side, which consider self-propelled particles. I'm not going to go into too much detail since I only have 12 minutes, but what I want to talk about is this idea of bounded confidence. So as I said, we can change who interacts with who and who is influenced by who. And we can have a limit on how far away you're going to be influenced by someone. So people will only interact and move towards opinions of those who already share a sufficiently similar opinion. So maybe you can think of this as a confirmation bias, or sometimes in sociology, I think it's called homophily, which is a quite a fair assumption. I think we can all agree that's one we would consider to be quite grounded in psychological principles or sociological principles. We can also introduce a stubbornness effect. So we know that people with more extreme opinions tend to be less influenced by other people and be a little bit less open-minded. And we can model this into our model by just linking the length of the confidence bound, so how far away they'll listen to people and be influenced by people, to how far away from some neutral points the agent is. So here the agent is moving away from the neutral point, and so the confidence bound, or how open-minded this agent is decreasing. So that can decide who agents listen to and who individuals listen to. But then we have to decide how much does the opinion shift based on the difference or the opinion, absolute difference of opinions. So the most simple assumption is this sort of linear positive influence. This is bounded, obviously, by the distance away from the other agent which is being considered, because in these sorts of models, we don't really consider an overshoot of, for example, if I have a friend who likes football, I don't like football, then I'm probably not in one step going to go and buy like £1,000 tickets to the FIFA World Cup or something. I'm more going to move into their position rather than overshoot them. So that's bounded for how far they can move. You can also have then, as you move further away, less of an influence. So as we are less alike, then I'm influenced less by you. I want to move less towards your opinion. And then you can also introduce negative influence, so repulsion. So this is a idea in literature. But one of the counterintuitive results is that opinion change actually can increase with disagreement for certain points, which is something which I didn't expect, but there is some evidence for this experimentally as well, which is quite interesting. So then that brings me on to our model. So we want to consider the most restricted form, basically, of the model possible. So you can think about these models in as many dimensions as you like. You can just stack as many different opinions as you like on top of each other and have them all related to each other or all unrelated. But we'll just consider a one-dimensional opinion space now, and with three agents or three groups of agents, where we have one agent at the neutral opinion, and then we have two extreme agents on either side, where the right-hand side here will say it's further away than the left-hand side. So here in this setup, we can set the confidence bounds. So we know that the neutral agent will listen to both sides, whereas the extreme agents, because as I said, the confidence bound decreases as the extremism increases, we can set it so that they don't listen to anyone, basically. So that's just shown here by these confidence bounds. So then we come to this oscillation mechanism that we try to look into. So this considers the distance away from the agent and the confidence bound, basically. So first at time t, the agent will move to the right because it's further away from the right, which again seems counterintuitive, but we'll go with it for now. And then at this new position, because the agent which has moved away from the neutral position, its confidence bound decreases with extremism, then it could decrease to the point where it no longer listens to the right-hand side, like this, and then moves back to the left-hand side, basically. So this obviously doesn't have to happen in just one step, but this is an idea of the sort of mechanism that could introduce oscillations into these sorts of models. Because most other models which try to capture this sort of non-steady state behavior, they have some sort of external shock which is put into the system, or some sort of noise term or randomness term as well. So I'm going to quickly introduce some maths. So basically here we're going to talk about an agent's opinion at the next time step is its current opinion, which is xi, and then the average of all the other opinions that it's listening to. So in the standard opinion dynamics model, which is known as the Hexman-Krauss model, this is every other agent. Then we can introduce the bounded confidence with this indicator function. So this only says that if they are epsilon distance away or less, then the agents will be listened to, and then they'll be counted as part of this influence. And if they're more than that, then they're not listened to. And so this at the moment is just what already exists. This is standard Hexman-Krauss and bounded confidence. We can then add in the influence function, which we talked about. So instead of considering each one equally and then just creating an average, we can have some function where we can tune it, as I showed before, where it scales the influence based on the distance. And then, then changing the bounded confidence so that instead of just a constant bound, the bound changes with the agent's position away from the neutral point. Okay, so basically, what we're saying is we're just taking the standard model and adding these two influence function and the extremism function into that. And we can recover the standard Hexman-Krauss model as well from this. So basically, the main result is we do find prominent sustained oscillations. So in a previous model of a different formulation of this, they had very small oscillations in multiple dimensions, which was basically quite interesting. But we wanted to, again, look at this very restricted version of the model, and we find much larger oscillations and a sustained going on for non-steady state solutions going on for infinity, basically. We also find that in this formulation, only, so for example, one agent on the extreme side of each side can have a large influence over a large group of agents in the middle. So you can have one agent on each side and then 95 agents in the middle, for example, which is what this one shows, which shows the outsized effect that extreme agents can have on the average opinion of the group as a whole. So I'm on 12 minutes. So basically, our main finding is that strong oscillations can arise in this very restricted deterministic system with as few as 3 agents. So this is interesting to us because this is a result that we haven't seen before, and it allows us to expand this class of opinion dynamics models to try and look at these results in more detail. So currently, if we have this mechanism, even though it might not be currently exactly correlated with what we see, it allows us to add something extra into the toolbox of opinion dynamics modeling. We do it without requiring as many conditions as in the original model. So the previous results I showed had some conditions on the minimum number of agents and things and minimum dimensions and stuff. But as I say, we have this very restricted model. And also what we find is that periodicity is more robust than we thought. So we were kind of fine-tuning our model to try and find this result, to try and prove that it exists. But then once we found this sort of result, we then tried some robustness checks and found that it was, quite robust. So it's quite robust to initial conditions and initial distributions of agents' opinions, for example. And then we have this without having to introduce any sort of internal noise term or anything like that. So I'm over time, so I'll just say the future work is that mostly we're just going to add into networks. So that's a very important thing in opinion dynamic models, where we don't just interact with everyone based on how close our opinions are, but our also pre-existing relationships and spatial relationships or online relationships, for example. And thank you for listening to my talk. I hope you have a positive opinion of my talk.